Right, so today we're going to be looking at moving to 3D, thinking about vectors. I made up this very fancy visual aid for you guys. So this is the two-dimensional system as you normally see it, right, with X pointing out in the X direction and Y pointing vertically. And if we're going to go to 3D, basically we need to figure out how to add Z into this mix. It goes perpendicular, so it's either like this or it's like this. And there's a choice made when you do that. So which way should it go? Well, what I just did there, that's the wrong way. And the reason for that, well, the way you can figure out why that's the wrong way is you take your right hand and you grasp the Z-axis with your thumb pointing in the direction of the arrow, right? And your fingers are supposed to curl in the direction where they send X to Y. And I don't know if you can see it, but I've got Y going to X as I curl my fingers. So I put it on wrong. Put it on this side. If I grip the Z-axis with my thumb going up in the air, well then my fingers curl from X to Y. Get that? So that makes it a right-handed system. If you have a right-handed system and you try to make the same check with your left hand, then you'll get, again, the fingers curl the wrong way. So it's not a left-handed system, it's a right-handed system. There's lots of things in the natural world that have a natural handedness like this. Anything with a spiral shape to it, there can be two different sorts. So DNA, for instance, has a right-handed spiral. Some molecules that are important in life have a handedness to them, so that a left-hand version and a right-hand version are actually distinct. I think the most famous example I know of that is the sugar dextrose. Dexter is actually the Latin word for right, and dextrose is the right-handed sugar molecule. There's also a left-handed sugar molecule called leftose, and they actually taste slightly different. You can tell the difference between them by their taste, but it's a minuscule difference, but it's still noticeable. The funny thing is dextrose works in your body, and you can use it for energy, and leftose does not. So if somebody could find a way to manufacture leftose in bulk, it'd be a perfect sugar substitute. I once read a sci-fi story about a guy who teleported, and he basically built some sort of machine that, like the transporter on Star Trek, and he went elsewhere, and then when he came back, he hadn't accounted for handedness. So when he came back, he was the wrong handedness, and none of the food that was accessible to him was the wrong handedness. It was all the right hand stuff that's here on Earth. So he eventually starved to death, which is kind of an unpleasant outcome, but yeah, there it is. Anyway, right-handed systems have a conventional way for drawing them, which we should talk about. Because so often you have to do things in the plane. What we'll do is start off with our traditional pair of axes, but the labels are switched. This is going to still be the x-axis, but this vertical one now is z. It tends to be the case that people like to use up for the z-axis. Then where's y going to go? Well, we need it to be right-handed, so you think about this. If you align your thumb with the z-axis and your fingers are pointing out in the x-axis, and then you try to curl those fingers of your right hand, they should be pointing in the y direction, which means y goes away from us into the board. So I'm going to write like a tiny y out there because it's off in the distance. Is that working? I don't know. But yeah, so X and Z, normal positions, Y, into the board, or away from you. Because honestly, when you draw something on a flat board, can you really tell whether it's coming towards you or away from you? Okay, so that's the conventional way to make a drawing of XYZ space. There's certain planes that you should be aware of in this space. For instance, see how X and Z together form something that's, other than the names, it's just like our old XY system. So that's called a coordinate plane. We've got the XZ plane. So I'll write that down. XZ, actually we don't usually hyphenate that. XZ plane. Like that. If like some scraps of cardboard, it would be oriented like so. Then there are also, other planes here that are coordinate planes. So the regular XY axes, right? What's the XY coordinate plane look like? Well, visually it's seen in perspective there, but it's a horizontal plane. And there's one last one of these. That's the, what's left? X and Z, X and Y. We need one that doesn't involve X and just has Z and Y. So what's the ZY plane? Well, it's seen in perspective right there, kind of at a funny angle, but it's really this one. It's the one that goes both vertically and away from you. So maybe it's a little hard to see. I should tilt it a little bit so you can get the idea. Okay, so these actually have equations that we should mention. I think visually the XY plane may be the easiest to think about. What is an equation for the XY plane? Well, it's weird because X and Y are free to do whatever you want if you lie in that plane. The only constraint really is that you need the Z coordinate to be, well, what value is the Z coordinate? 0. So that turns out to be the whole equation. You just say Z equals 0, which I think to most people feels a little weird. You're like, okay, Z is 0, but what about X and Y? And just try to get used to the zen of this. If a variable goes unmentioned, then it's free to do whatever you want. Right? So the fact that X and Y are unmentioned is what makes this actually be a plane, rather than, a lot of people might think Z equals 0 is that spot right on the Z-axis where the coordinate value is 0. But Z equals 0 is not. It's that spot together with any other spot that has a Z value of 0. So yeah, you get a plane when you set one of the variables equal to 0. Which variable should we set equal to 0 to get the XZ plane? That's the one that's oriented flat to you. Yeah, well that's, it's maybe easier than you think, because this one is called the XY plane and its equation is Z equals 0. The thing that you need to set equal to 0 is the one variable that's not mentioned here. So if you're looking for the XZ plane, that's when Y is equal to 0. And the ZY plane, that would be when X is equal to 0. Now when you put these planes together, and I can only do this crudely because I tried doing it with duct tape before and it didn't really work that well, but these are those like separators that go into a carton that's holding glass bottles. So they're designed to engage with one another and form like a grid. But that's perfect because that gives us what the ZY and the ZX planes. And the only thing extra we need is another plane that goes like that. I tried duct taping it like so, but I couldn't make it happen. It just kept falling apart. But I think you can visually imagine it. Just if I could push this cardboard right through the other pair of things, we'd get an object that shows all three of the coordinate planes. And the one that we're sort of most interested in is when both X, Y, and Z are all positive numbers. The area that, I shouldn't say area, but rather the volume that you're seeing right in here, that is where X is positive and Z is positive, and on the other side of the board, that's called octant 1. Or more typically the first octant. It's where X is positive, Y is positive, and Z is positive. Now, when you did ordinary two-dimensional graphing, you remember doing this, you had the axes, and then we called this the first quadrant, and this one was the second quadrant, this one was 3, I think it went this way. 1, 2, 3, and 4. If with octants, you would have 1 through 8. Is it clear to everybody that these coordinate planes would divide space up into 8 regions? We don't have a system like this for numbering the octants. It would be kind of a pointless thing to engage in. But we always talk about the first octant, there. Don't worry about this kind of thing for the rest of them. What you can do, though, is sort of have a little shorthand. What I personally do, anyway, is a little shorthand for these octants based on the sign of the x, y, and z coordinates. So the first octant, I would call that plus, plus, plus. There's also things like minus, minus, minus. That was supposed to be 3 minuses. Right, that would be kind of diagonally across from the first octant. Every number negative. But you could also have the plus, minus, plus. I don't know. That's a way to distinguish the various octants, but there is no scheme like that where they number them the way they did with quadrants. If you're we should probably try to expand our repertoire a little bit beyond the coordinate planes and be able to talk about generic planes. A first step in that direction is to at least get ourselves the ability to write equations for planes that are sort of in the square positions, horizontal planes, and either of the two kinds of vertical planes. So suppose I wanted to have a plane that was not the xy plane, but one that was shifted up in the air and went through the z-axis at some point. Suppose I want to cut the z-axis right here at z equals 3 and get a plane there that's like another copy of the xy. Oh, I should make it look like the xy. That should be parallel to there, right? I'm kind of drawing this little thing like a window frame or something to give you the idea of the plane, but it's an infinite plane. So I don't mean for it to be just that little square. So it keeps going in all directions. How do you actually give an equation for such a thing? This infinite plane that spreads out where the z coordinates are all 3. Yeah, that's right, z is 3. The equation for this guy is simply z equals 3. And you can do similar things for the types of planes that are vertical. If I wanted to go 2 units out along the y-axis and then create a vertical plane that was parallel to the xz plane, it would, at least a piece of it would look like that. That would be y equals 2. What else? There'd be, x equals 7 out here. That's a tougher one to draw, isn't it? I think those little window pictures help a little bit in sort of visualizing the orientation of the thing. What did I say this one was? X equals, I don't know. If that's 3, then yeah, maybe it's 6. 7's close enough, right? We're just making a sketch. Okay, so one thing I didn't have on my notes here, but I should point it out to you. We can plot points in 3D pretty well. It's not perfect because there's going to be certain points that will need to be drawn in the exact same location. Because, we're trying to represent something that's 3-dimensional in just a 2-dimensional plane. But nevertheless, you can draw points by thinking about their coordinates. Suppose I wanted to draw the point P has coordinates 1, 2, and 3. What I would do is think about moving separately in the x, y, and z directions and sort of trace those paths. So go 1 out along the x, then go back, I erased y, sorry. Go back in the y direction 2, and finally go up 3. And there's your point. So you see this little triple of two horizontals and then a vertical line that arrive at 1, 2, 3. So that's not a bad way to get a visualization of where 1, 2, 3 lies. Erase the y-axis label and part of the z-axis there, didn't I? Okay, let's try to get a second point on the screen, on the board in front of us. How about Q is 4, 5, 5. So that would mean go out 4, that's to there, then go back 5, try to go parallel to that line, right? And I think in the Y direction, things are a little foreshortened, so that's probably 5 right there. Nope, I don't want to draw the point there because I also have to go 5 vertically. So out, what do we do again? Out 4, back 5, and now up 5. I think that's about like so. So that's, oh, I didn't put the label on it. P is 1, 2, 3. Q is 4, 5, 5. And there's a vector that goes between those guys. They do a different color for our vector. This is just a three-dimensional version of what we did last time, but that would be the vector PQ, whose initial point is P, whose Q terminal point is Q. What I want to do is generalize the idea of magnitude, which we had in 2D, and so distance between points is the same thing as the magnitude of the vector, but we want to do it in 3 dimensions. So how far apart are P and Q? That's really the question. And it's got a simple answer. Basically the same formula works that comes out of the Pythagorean theorem. The sum of the squares is equal to the square of the other side. It just has 3 squares in it instead of 2. So how far apart are these guys? The distance is going to be the square root, because really d squared would be the sum of the squares, but square root of the x coordinates differ by 4 minus 1. The y coordinates differ by 5 minus 2. And the z coordinates 5 minus 3. So what is this number? 3 squared is 9. That's another 3 squared, so that's another 9. And 5 minus 3 is 2. 2 squared is 4. So that's not such a nice number. I probably should have worked it out so it came out prettier, but this is square root of 22. 18, 4, yeah, 22. I guess we could get a calculator out and find it as a decimal, but let's just leave it like that. So there's sort of 2 ways to proceed like we just did. If you know the points involved, you could say the magnitude of vector from P to Q is square root of 22. That's fine. The distance between the points is the same thing as the vector's magnitude. If, on the other hand, I just told you that V was a vector, I don't know, let's make it simple, 1, 2, 3. Then what's the magnitude of V? Well, you just do the same calculation we just did, but with 1, 2, and 3 in it. You don't need to do any subtractions because you've already, essentially, you've got a vector that's representing the difference between terminal and initial points already. So this guy's length would be square root of 1 squared plus 2 squared plus 3 squared. 9 and 4 and another 1. 13, 14, square root of 14. So a couple of examples of taking magnitude. There's sort of 2 different versions of it, right? There's the one where a vector is given by a pair of points, and the other one where the vector is just given by its coordinates. All right. Once you've got that magnitude idea down, though, or really the distance formula down, the idea that you can just generalize by adding one more sum end to the sum of squares there, you get a freebie. What would you call the set of points that are exactly 1 unit away from Q? And if I look at a point here like Q and say everything that's 1 unit away from it, well, it's a little ball, isn't it? So you can get the equation of a sphere, which I'm going to try to sketch by drawing like lines of longitude and latitude around it, but there's a little sphere centered of Q. It's actually defined precisely by saying the distance formula gives you 1 if you put in the point on the surface of this thing and the 455. So what do you call a point on the surface of this thing? Well, you know, it's funny because you get to name it. You call it XYZ. Well, I tried to write XZZ. Did you see that? So XYZ is a generic point, but we want to constrain it so that that point lies on the surface of the sphere, that it's 1 unit away from 455. So just write down that condition, that 1 will be equal to the square root of, what's it look like? I guess I'll do 4 minus x squared plus 5 minus y squared plus, well, you can see what the last one is. I'm off the edge of the board, but it would be 5 minus c squared. All right, I'll just... I had to take the square root, break a line on a square root feels really strange to me, but I just did it. I don't know. Yeah, so that is actually a reasonable formula for it, but it's a little bit unnecessarily complicated by the square root. You could have just said, well, basically you could just square both sides of this. So can I say this to you in general? Suppose I have a sphere that has a radius known of, say, r. And its center is some known point. I'm just going to use A, B, and C for the coordinates of the point. Well, what is its equation going to be? Let's do the thing I just mentioned. The distance, of course, will come out to be r rather than 1, but we're going to also square both sides of that. So r squared is equal to, what do I have? X minus a quantity squared plus y minus b squared plus z minus c squared. This is a little hard, but not crazy. You know, it's just 3 terms, they're quadratics, and each variable has subtracted from it the corresponding coordinate from the point that's at the center. So the shape of that is pretty reasonable. Okay. Oh, there's a distinction to be made about the difference between balls and spheres. I don't think in ordinary usage anybody makes a distinction, but in the math world they do. They specifically use the word sphere for the surface. So a sphere is the surface of a ball. I guess I should capitalize that one too. Okay. So really the ball would be, well, with a less than or equal to, and the sphere would be this equal to. So I guess I like it to write it this way. The distance formula with the stuff we just had in it if the distance is less than or equal to r, that's a ball. If if I wrote the same thing with an equal sign, and let me just say dot, 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 the same formula, that would be a sphere. Well, you know what? The symbol people usually use for that is quote, the thing above, quoting the thing above, sorry. All right, so we've made that distinction. There's a little section in the book where they talk about doing the vector operations in 3D. And it feels really repetitive to me. Remember we did things like u plus v, and in coordinates that was u1 comma u2 plus v1 comma v2. So you've got, you know, what you have to do is add the u1 and v1 and add the u2 and v2. The sum of the ones is in the first position, and the sum of the things with twos on them is in the second position. That's what we did last time for adding vectors that had length 2. If we're going to add vectors that have length 3, it's really not much different. It's just that they have length 3. So I'm going to try to, I'm going to just use a little judicious erasing to make that happen. We'll fit u3 in here. I had to cram it in a little bit, but it fit. And then we'll put v3 down there. Well, the last one, I guess I can't just cram it in, but what is going to happen? I mean, we're adding a length 3 vector to a length 3 vector. Do you not expect to get a length 3 vector here? And its coordinates will be the u3 and the v3 added together. So you can extend the definition of adding that we did for length 2 vectors to having length 3 vectors, and quite, I think it's pretty clear. You can have length 17 vectors if you want it, and if you want to find out about, you know, actually working with much larger vectors, you're going to need to take linear algebra. For our class, we'll stop at 3, but I hope you see that this process could be generalized to much higher dimensionality. I'm not going to go over what it looks like to subtract, because, you know, just changing a bunch of symbols, but scalar multiplying, it's very similar. Instead of distributing it across 2 things, you'll distribute it across all 3 things. Finally, we did already talk about the magnitude of vectors. I got this out of order on my notes, but unit vectors. So anytime you have a vector, you can divide by its length and get yourself a unit vector. So given any v, the vector that you get by taking v and dividing by the length of v is a unit vector. And it points in the direction, whatever direction v is. Now, I'm feeling just a tiny bit guilty right now because I don't know if we talked already about dividing a vector by a scalar. We talked about multiplying by a scalar, but never dividing by a scalar. So if that makes you concerned, that's good. You should be that careful about the way you're thinking about things. But this is easy to resolve. You could also write this thing. Maybe I will write it instead of that way. Write it as 1 over the length of v times v. Is that better? Except this is pretty handy shorthand, right? To just say, okay, we can divide by, v by its length. Let's do an example of this. If we have v is, how about 3, 4, 0, right? Then the length of v is going to be the square root of 3 squared is 9, plus 16 for the 4 squared, and 0, the 0 squared. And that's 25, so you see that this is length 5. Okay, so that means if I just divide every entry by 5, I get a unit vector. So it would be 3/5, 4/5, and, well, 0/5. I think I'll just write 0. There, that thing is a unit vector. There's actually tons and tons of unit vectors because any vector at all can be, we can run this process on it and get a unit vector. But there are 3 that stand out in particular. And those are called I, J, and K. So in the normal representation, when I draw the coordinate axes like that, this first one that points in the x direction, that's the vector I. And it's supposed to be a unit vector that points in the x direction, so figuring out what its coordinates are pretty easy, right? J is the one that points into the board. Vector J has a 1 in the y position. So it's 0, 1, 0. And vector K, that's maybe the obvious thing from after I and J, that's got a 1 in the z coordinate. So it's 0, 0, 1. Now, a lot of people find these choices unusual, and so it bears a slight, what letters they chose to use for those unit vectors in the various coordinate directions. There is actually a good explanation for it. It's because I was the imaginary unit. Remember I is the thing that's square is -1, or I'll just write it I equals the square root of -1. It's because there was a guy back in Ireland in like the 1800s who was trying to generalize this, because basically having the square root of -1 around meant that you could multiply pairs of things. You could take things like the number a plus bi, a complex number, and you could times it by a different thing that's a complex number. You just FOIL roll that together and use the fact that I squared is -1, and you can go through the algebra if you like and turn that into another thing that looks like a pair. So pairs could be multiplied by, a pair can be multiplied by a pair. That is, there's a way to make a product on points in the plane, effectively. And this guy Hamilton wanted to see if he could do it in 3 dimensions. So he called the extra things I, and just went from there, J and K. Now he didn't have the vector hats on him. He literally called them I, J, and K and thought of them as other square roots of -1s. And that led to a thing called the quaternions. Now you might be thinking, wait a minute, the word quaternion sounds like 4 something, and it is 4 something. It turns out what he wanted to do was figure out a way to multiply triples, and it can't be done. But he could just bump things up a little bit, and he could multiply 4 tuples. So a quaternion is something that looks like this: a plus bi plus cj plus dk. And when this guy Hamilton had this flash of insight that let him realize he could use expressions like that and kind of way to multiply 4 tuples with I, J, and K all being square roots of -1, and there's other relationships. He got so excited he went out and defaced a bridge in his local area. He carved the equations for the quaternions into a bridge, which I still want to go to Ireland and find this spot and see if you can still see his graffiti. Okay, so that brings us to the end of section 13.2. I'll be along more soon with 13.3. See ya.